Right, we are discussing chemical bonding. I would love to remind you, right, you have been through this chapter, right, in your earlier classes, right? Let me understand what exactly is a bond first. You all have a perception of a bond, no dispute on that. But technically from here onwards, a bond must be viewed, the bond must be viewed as a force. A force that will bind two atoms or ions or, the fundamental particles to form a molecular system. So atomic system forming a molecular system, and the force that binds these atomic systems can be called as a bond, right? So bond is basically a force, you must understand that. When you say it is force, then we don't have a single force, you have several forces. One is an ionic force, electrovalent bond that I'm referring to, and your electrostatic force. And then you have your covalent force, you have a metallic force, you have an induced force, you have types of forces. When you have types of forces, then we can expect types of bonds also. And the first thing is the most strongest force, that is the electrostatic force. And we are discussing what ionic bond, you must understand. And I was telling you several aspects of ionic bond, but remember, most of the ionic substances are nothing but solids. They are crystallized as solids in the laboratory. When they are crystallized as solids in the laboratory, it is, they will be attaining a definite shapes. They will be having a definite shapes. And we cannot discount these shapes and go away, right? Because each ionic substance will take a definite shape. You must understand. These shapes, what they are taking is not our choice. They are sitting in that shapes because where they experience minimum repulsions and maximum attractions, and wherever there is minimum repulsions and maximum attractions, their maximum energy is lost, right? So if you are crystallizing an ionic substance, say X, it has a different shape. Y, it has a different shape, and these shapes are not prepared by us. The moment they are crystallized in the laboratory, they are taking those shapes, and the reason for that, if someone is asking you why sodium chloride is face-centered cube and why potassium chloride is body-centered cube, if someone is asking that, then you must be in a position to tell them that these positions which are occupied by the ions in an ionic compound are the positions where they experience minimum repulsions and maximum attractions. You must understand, right? And such a situation where you experience minimum repulsions and maximum attractions is when the system loses maximum energy. And when the system loses maximum energy, that's where the system is said to be what? Stable. You must understand that, right? So it's all about stability. Whatever we do in chemistry is all about stability, achieving stability. Atomic systems combining to form molecular systems is all about what? Achieving stability. You must understand, right? So what we cannot discount is ionic compounds will be attaining definite shapes, right? And these shapes must be understood well in detail. So that's what I said, the infinite, regular, three-dimensional arrangement of these ions in space is called a space lattice. So if I can repeat, the infinite, regular, three-dimensional arrangement of ions in space can be called as what? Space lattice. So since it is an infinite arrangement, what we have done is, instead of taking this infinite arrangement, since it is infinite, we have taken the simplest sample of the lattice. We have taken the simplest sample of the lattice, and I was actually comparing this with a brick of a wall, and then what you do is you repeat at regular intervals, then I think it generates the shape of the entire lattice. So instead of speaking in terms of big lattice, infinite number of atoms, what we have done, we have taken a simplest lattice, and that we call it to be unit cell. This is what we were discussing yesterday in the previous class, right? And unit cells, what are they? They are simplest samples of a lattice. So whatever language you use for unit cell is applicable for what? Lattice. So what is FCC? What is BCC? What is face-centered cube? What is body-centered cube? If someone is asking you, then you tell that those are types of unit cells. You must understand, right? And if that is the case, it's a common sense, since it's an infinite arrangement of ions in space. If you take a simplest sample, then what happens is a lattice as a whole will be having infinite number of unit cells. You must understand, right? A lattice will be having infinite number of unit cells. So what I'm basically telling you is a unit cell cannot be isolated. It is not isolated. You cannot take that and put it in your pocket. No, it's not isolated. And also understand that a unit cell is surrounded by several other unit cells also. They're actually surrounded by several other unit cells. So a unit cell is not isolated. It is surrounded by several other unit cells because it's an infinite arrangement in a lattice, and we are considering a simplest sample, right? This understanding must be there. And also coming to the unit cell, a unit cell is a cubic lattice, right? A unit cell will be looking like a cube, right? A cube will be having these points, 4 points. One is a body-centered point, the other is an edge-centered point, the other is a face-centered point, and you have what? Your corner points, right? So if you look into the face-centered points, it is 6. Corner points are 8, so it is 14. Body-centered point is 1, that is 15. And then you have edge centers, that is 12. So 15 plus 12 is approximately, it is 37, right? So you have 37 points which you can see in a unit cell. But what is surprising is all these 37 points are not belonging to one unit cell at all. They are actually shared by several other unit cells because a unit cell is not isolated. The unit cell is not isolated. The unit cell is surrounded by several other unit cells. So we have calculated each and every point's contribution to a particular unit cell, whether it's a body-centered point or an edge-centered point. A face-centered point will contribute only half. A corner point will contribute 1/8. A body-centered point will contribute as a whole. And remember that the edge-centered point will be contributing 1/4 only to the unit cell. So there are questions on this. And remember, if you have done that calculations, then final conclusion what we had in the previous class is basically 1 mole of unit cells, 1 mole of unit cell will be having 1 mole of sodium ions and 1 mole of chloride ions. Or simply you wanted to take 1 unit cell, only 1 unit cell, forget about 1 mole. 1 unit cell, then it will have 4 atoms of what? Sodium and 4 atoms of chloride ions. You must understand. Even though 37 points are available to a unit cell, but total sodium ions are only 4 and total chloride ions are only what? 4. That's what it is. That's what is the point of discussion. That itself is a point of discussion. So if you take 6 into 10 power 23 unit cells and find its mass, it comes to 234 atomic mass units. That's what is the discussion yesterday in the previous class we made, right? So why all this discussion has cropped up is simply because ionic substances are solids. They are basically solids, right? They attain a specific shapes, and each ionic substance will be having a specific shapes, and those shapes are not our choices. They are only sitting in their positions because they are comfortable having minimum repulsions and maximum attractions. Minimum repulsions and maximum attraction gives what? Maximum energy loss from the system. And they achieve what? Stability. And the lattice is there, and the unit cell is there. And remember, specifically for NaCl, which will be asked in exam, right? So the total mass of 1 mole of unit cells of NaCl is basically 234 atomic mass units. That's what we were discussing, right? And coming to the next point, what we will do is we will determine the lattice energy, and the basis will be the Hess's law of constant heat summation. That is our point of discussion, right? And if you ask me, let's recollect, if you ask me what exactly is lattice energy, what exactly is lattice energy, then I consider it is an average force. It is an average force. It's basically an average force that binds. The average force, if someone is asking what is lattice energy, I consider this to be an average force, right? That binds oppositely charged ions in a lattice. So ionic substances are basically made up of ions, and the average force that exists between these oppositely charged ions, I consider it to be a lattice energy, right? So otherwise also you have the 2 ways to understand the energy released when a lattice is formed. So I was referring, that's why I asked you to listen to me carefully. I was telling you that an ionic substance will be having a specific shapes, and those specific shapes are not our choice. They are formed on their own. And what is the criteria? What is the best thing happening to that lattice is minimum repulsions and maximum attractions. Right? That's when the lattice is stable. That's what I'm telling you. So the energy released when a lattice is formed is also called lattice energy, or you can actually say the reverse. The energy required to actually separate the lattice into its constituent ions, because the lattice will be containing oppositely charged ions. So the energy required for you to separate them is also called what? Lattice energy, you must understand. Right? For getting into a mathematical expression, the best way to understand lattice energy is nothing but the average force. This is the average force that binds oppositely charged ions in the lattice. Then when you can consider that, then lattice energy is nothing but force. This is equal to Q1, Q2 by RC plus RA into a constant. You must understand that's how the lattice energy can be considered, KQ and Q2 by what? RC plus RA, where RC is the radius of the cation, where RC is the radius of the cation, right, and RA is the radius of anion. You must understand, right? If this is the cationic charge, this is the radius of the cation, this is the cation, and this is the radius of the anion. So the total of this is RC plus what? RA, that's what he is writing. And what is Q and Q2? Those are the oppositely charged ions charge. It's not the sign, it's the magnitude of the charge which these oppositely charged ions are possessing, right? So from this, as a mathematics student, what I understand is lattice energy will be directly proportional to the product of charges, and lattice energy is inversely related to the radius of cation, and lattice energy is inversely related to the radius of anion. That's how we have a mathematical expression, and you can get through the mathematical expression only we understand when the lattice energy is nothing but the average force that exists between what? Ions in a crystal lattice, right? That is how it is. So remember these equations, and remember also one or two things which I would like to quote with respect to lattice energy. Observe carefully here. Now what we do, since we know the definition of what? Lattice energy, why don't we determine the lattice energy? Why don't we determine it, right? How do you determine the lattice energy, and are there any laws behind it which we will be using in determination of lattice energy is the question, right? So let us go and determine the lattice energy. First of all, you understand that lattice energy is denoted by U. So whenever you're opening your textbook or going through any science books, when you look at U, that U is basically designated for lattice energy. You must understand. The lattice energy is basically denoted by U. Now what we are trying to do, we know what is a lattice. Look at the sequence in which I'm actually lecturing for you. First we said that ionic compounds are solids. When they are solids, they will have shapes. That shape is determined by the lattice. You know what's a lattice? You know what a unit cell is, right? And then we made an expression for lattice energy. Now we are trying to determine what? Lattice energy. That's what we are doing. You should know what we are doing exactly first, right? So look into the sequence once again. I say ionic substances are solids. They attain definite shapes. The shape is a lattice. And then we went for unit cell and we expressed what is the expression for lattice energy, and now we are trying to determine what? Lattice energy. So we are actually basically determining what? Lattice energy, right? And lattice energy is denoted by what? U. You must understand. What we will do, we will take a specific example for determining the lattice energy. We'll take a specific example for determining what? The lattice energy, and then go for the other substances. What we will do is, we will go in for that. Determination of lattice energy of the crystal lattice NaCl. Let us take NaCl and determine what? The lattice energy, right? For that, how do you do it? Now remember one thing. What we will do is, we'll get into the lab here. We'll get into the lab and we'll sit in the classroom, and then we wanted to compare that activity what we have done in the lab and done in the classroom. Let me give details of it. Now assume we are preparing NaCl. right, our teacher is lecturing how his NaCl is formed. And the lecturing is going on in the classroom. That means we are getting into the theory of how NaCl is what? Formed. How NaCl is formed, this theory is lectured by your teacher in the classroom. After the lecturing, I go into the laboratory to prepare NaCl. Right? How do we prepare? There is no lecturing there. What he's doing is he's taking the sodium solid and exposing it to chlorine gas. Exposing it to chlorine gas. Then NaCl is formed. Right? What we are doing in the classroom is the theory where our teacher is explaining us like how sodium chloride is formed, what are the various steps involved in the formation of sodium chloride. These things are very detailedly explained in the classroom. After that, we venture into the lab and just expose the sodium to a chlorine gas and you got your NaCl. Right? So what I mean by this, for determining lattice energy of NaCl, what I'm writing is, look into this. The direct step. Please understand, the direct step. I would like to call this to be an experimental step or the lab one. You get into the lab, how do you prepare sodium chloride? Is you take the direct step. You take the sodium solid and expose it to with chlorine gas, then you're supposed to get NaCl. That's what you need to do. That's what you need to do. It's as simple as that. Sodium is stored under kerosene in the laboratory. You take out the sodium and expose it to chlorine gas, directly the sodium chloride is formed. That's a single step. And if you can balance this is half chlorine. And when sodium chloride is formed, remember that there is a great love between extreme left and extreme right elements. After all, it's sodium which is placed to the extreme left of the periodic table and chlorine to the extreme right because they are halogens and they are natural lovers. And when sodium and chlorine are loving each other to form NaCl, naturally the process will be exothermic. Any natural love's energy is released, right? It's an exothermic process. So I can simply say plus Q, that is heat evolved. That is heat evolved. Now the sign conventions might be somewhat confusing. Well, I would like to clarify this and take some time in explaining this to you, right? Within the equation, if you're writing plus Q, that means it is heat evolved. It is basically heat evolved, right? Remember that it is heat evolved. Within the equation, if you're writing plus, if you write plus, it is heat evolved. But sometimes what happens is he writes it outside, the heat of reaction, what we call. The heat of reaction is something written like this. He writes it outside the equation, that is delta H. Then he writes it's minus Q kilocalories. It's minus Q kilocalories is what he writes. Both are same. Within the equation, if you're writing, the sign convention must be positive and it's heat evolved. And if you wanted to write the heat of the reaction, then delta H is the heat of reaction, which is written as a minus sign because you're actually removing it outside and minus Q. So delta H is negative, is exothermic. Within the equation, positive is also what? Exothermic. So this is the two ways to express what? Exothermic. This is also exo within the equation if it is plus. If you wanted to write outside, yes, you can write it, that is exothermic reaction. Right? So what we are doing, don't forget that, what we are doing, don't get confused. What we are doing is basically we are determining the lattice energy of ionic substances. We are determining the lattice energy of ionic substances. Now the first thing is we went to the lab, we got into the lab, we have taken sodium solid and exposed it to chlorine gas and you have sodium chloride formed. It is so simple because they love each other. The reaction is exothermic. Within the equation, if you write it, it's heat evolved. And then it's minus Q kilocalories. Now the question is, that is the direct step. That is in the laboratory, that's how you do. Now what we have done, we have come into the classroom. In the classroom, you don't have sodium solids and chlorine gases where you can expose it. Our teacher is now getting into theory. Now she or he is explaining how the sodium chloride is formed. And what I will write it is like this. The above step, the above single step this above single step, what we have written, can be theoretically, right? The above single step can be theoretically divided. It can be divided into 5 steps. So what we have done, we have prepared the sodium chloride and it has attained the face-centered cube, right? Because the shape of NaCl is what? Face-centered cube. And then we entered the classroom and we are asking our teacher, can you please explain how the NaCl is formed? Then what he is doing is, she's telling us that the above single step, this one, can be theoretically divided into 5 steps. And what are the 5 steps? What he's telling is, 1, he first wanted to sublimate or sublimation energy of sodium. Look into the 5 theoretical steps which I would like to explain this to you. 5 theoretical steps. Sublimation energy of sodium, and then it was telling us ionization energy of sodium, right? And 3 dissociation energy of chlorine molecule. Look into the 5 steps. I would like to give details, but understand what we are doing is the above theoretical step which you have done in the laboratory where the sodium chloride is formed is now split into 5 theoretical steps, right? This is done in the classroom. So I'm actually basically comparing the classroom lecturing versus what? The thing which is done in your laboratory. That's what we are trying to do. So remember, this single step is divided into 5 steps. Sublimation energy of sodium. Then I have ionization energy of sodium. Then I have dissociation energy of chlorine, 4. Then it is electron affinity of chlorine. This is 1. And then 5, lattice energy of NaCl. So you look into this. So in the classroom, we need to discuss 1, 2, 3, 4, 5 steps. And these I consider it to be theoretical steps. So that's a direct step. So that is a direct step. And this direct step in the classroom our teacher was discussing huge. And it is divided into 5 theoretical steps. Right? And now, what is all this we are doing? Why are we doing all this? Why are we doing all this? Don't forget that. Why are we doing all this? Why are we discussing all this? Basically what we are doing is, we are actually determining the lattice energy. More specifically, we are trying to determine the lattice energy of NaCl. Is there a procedure? Is there a way? The answer is yes. We have a way. We have a way. So for that, go to the lab first, prepare the ionic compound, and then come back and then discuss how this ionic compound is formed in your own way. You split it out into theoretical steps. And as far as NaCl is concerned, your teacher was discussing huge, and it is actually 5 theoretical steps it has. Right? Let us explain all these 5 theoretical steps, and then finally don't forget that we need to determine the lattice energy of NaCl. Right? Observe carefully. Watch carefully. What we are doing, determination of lattice energy of NaCl, and lattice energy is denoted by U. Determination of lattice energy of NaCl. So what I'm doing here, the direct step. Now when I say direct step, this we are doing it in the laboratory. Right? This is the direct step. And what we are doing, sodium solid, which is stored under kerosene in the laboratory, because when you expose that to air, it forms compounds with explosion. So sodium solid, and then you have your chlorine gas exposed, then it forms NaCl solid. Right, just balance it. and plus Q, which is nothing but the heat evolved. And that is exothermic. Mind you, within the equation, if you're writing positive, it is heat evolved. And if I can take delta H, that is the heat of reaction, then we call this to be minus. So within the equation, plus is a sign convention, we call that to be heat evolved. Sometimes it is written outside as a heat of reaction, then it is written as a minus, but both ways of representation is for exothermic reaction. If you don't remember the sign convention, you're supposed to go wrong. You will be going wrong. So you should be carefully observing it, right? Once more, I wanted to repeat. Within the equation, if you're writing it plus, then it is heat evolved, exothermic. Sometimes it is written outside, that is the heat of reaction, which is written as minus Q. But remember, outside equation negative and within the equation positive, both represents what? Exothermic reaction. It's only a convention. It's not a concept. It's not a concept. It's just a sign convention which everyone must follow, right? That is the case. And what I'm writing, the above step divided into 5 theoretical steps. The above step is divided into 5 theoretical steps. And let me take up one by one and then get into the discussion, right? Observe carefully here. The very first step is, first of all, sublimation energy of sodium. Sublimation energy of sodium. Now, why all this is getting into why sublimation and what I'm doing? Remember that if you wanted to prepare sodium chloride, our teacher was telling that first of all it's an ionic compound. For ionic compound, you should ensure that electrostatic forces prevail between these two ions, right? You should have an oppositely charged ions. Now, in oppositely charged ion, one is a cation, that is Na+, and to form a cation, first of all, and then you form a cation, you need to remove the electron And removing the electron, the extrication of electron requires energy. That's called ionization energy, right? And if you actually recollect the definition of ionization energy, I would like to recollect it for you, then it is the energy released. It is the energy released when electron is removed from a neutral gaseous atom. So the definitions are important. You just can't discount it. So what we are trying to do is we wanted to prepare Na plus and we wanted to prepare Cl minus. And when you have oppositely charged ions, you have electrostatic forces and sodium chloride is formed. That is how theory says. What is what theory says? And to prepare Na plus, you need to remove an electron. You need to kick an electron from sodium. And that kicking of electron requires energy. And that energy is ionization energy. So what you do is, if you look into the definition of ionization energy, it's energy required to extricate an electron from neutral gaseous atoms, right? So before you remove the electron, first of all, you should have a neutral gaseous atom. Neutral gaseous atom. That means you're clearly telling me, first of all, that go and sublimate sodium. So you have a sodium solid, then you straight away convert into sodium gas, and this is what is referred to be a neutral gaseous atom. So the sodium solid, it's straight away converted toward gas without undergoing the liquid state. That's what is called sublimation. And this conversion of solid to the gas is not magic. It requires energy, right? Requires energy. So it's basically, I can simply say minus S, and this is heat absorbed. And this is endothermic. It's basically endo. It's basically endo. So within the equation, if you're putting a minus sign, within the equation, if you put a minus sign, that indicates it's an endothermic reaction and heat is absorbed. It is heat absorbed, right? And outside that, if you wanted to write the heat of reaction, then delta H is equal to plus S. You must understand, plus S kilocalories. Plus S kilocalories. So outside the equation, if it is plus, it is endo. Within the equation, if it is minus, it is endo. So within the equation minus and outside plus, both represents endo sign convention. You must understand it's a convention only, it's not a concept. So before kicking the electron from sodium, you must be sublimating the sodium. That is, first convert the solid to a neutral gaseous atom. And now this is the sodium gaseous atom, you must understand. For that, heat is supplied, and that is what I'm referring to the sublimation energy. Now the gaseous sodium atom is ready for you. It is basically ready for you. From that, you try to remove the electron. Removing the electron is nothing but the ionization energy. Watch here. Ionization energy of sodium. So what you do is you take this neutral gaseous atom, sodium gas, kick this out, one electron, Na plus, remove an electron, and for this energy is absorbed. And if you wanted to write it outside, then please write it outside, and this becomes plus I kilocalories. You must understand that since it is an endothermic reaction, right? So now I have sodium ion ready. The sodium ion is prepared for you. And this sodium ion is now searching for what? Chloride ion, which we need to prepare. And then once the sodium ion and what? The chloride ion are formed, no one in the world can stop them from combining. And then the energy is released, and that's what I refer it to what? The lattice energy. You must understand. Right? So the sodium ion is ready. So when you wanted to prepare a sodium ion, what theory says is first of all convert into gas. You convert that into gas, then kick the electron from it, and then it is Na+. Now coming to the third step. Now let's turn the focus to chlorine. Let's turn the focus to chlorine, because now the sodium ion is ready searching for what? Chloride ion. But what happens is you don't have chlorine atoms at all in chemistry, because chlorine atom is highly reactive. You only find chlorine molecules. You only find chlorine molecules because chlorine is so reactive, it combines with other chlorine and it is existing as a chlorine gas. So what you do is you take a chlorine molecule, dissociate into atoms. That is the first fundamental thing you need to do, right? So that's why I write it's basically dissociation energy of chlorine molecule. So it's basically dissociation energy of chlorine molecule. You must understand. So what is dissociation? This is the chlorine molecule, two atoms are there. You need to break this to two chlorine atoms. To two chlorine atoms. When you break it, you require some energy, and that is what you require it. So it's basically, this is called the energy required is what? D, which is called dissociation energy. What it is? Dissociation energy. So the energy required to break one molecule of chlorine to form two atoms of sodium, the energy required is what? D. But remember, we just wanted only half chlorines here. We just wanted only half chlorines. So for one chlorine molecule, the dissociation energy is D to convert this into chlorine atoms. But here we require only half mole. So for one mole of chlorine, if it is D, for half mole of chlorine, it will be D by 2. It's D by 2, right? So we require only half moles of chlorine. So dissociation energy of chlorine, if I can put it, half chlorine atoms, if they divide, then you get only one chlorine atom. And the energy required is minus, because you are actually giving energy, so it is heat absorbed. You must understand, and it is endo. And if you wanted to write it outside, then delta H is plus D by 2. You must understand. It's plus D by 2. You must understand that. Right? Why all this is happening? Because the sodium is ready for you. It is ready. And it is looking at what? Chlorine atoms, Cl minus atoms, you must understand. And we are trying to form Cl minus. For that, there are no chlorine atoms available. It is chlorine molecules that are available. So we are trying to break the chlorine molecules, and we require only half moles. For 1 mole it is D. For half mole it is D by 2. So the dissociation energy we required is what? D by 2, you must understand. So the 3 steps are finished. Now the remaining 2 steps, let us actually go and check it out. The step 4. So step 4. Step 4. Now you have chlorine atom in your hands. Look into this. This is the chlorine atom ready for you. Earlier it was not. We prepared the chlorine atom. And chlorine being a non-metal, now what we do is we need to prepare Cl minus, right? We need to prepare Cl minus. And the electron vomited by this sodium is now taken away by chlorine. This chlorine atom is now taking an electron, and it loves like hell, because chlorine loving electrons is maximum in chemistry. No one can love electrons like chlorine. It is first. So when I add electron to chlorine, it's actually catching like this. It's basically catching it off. And when you catch, it's a natural love. When it's a natural love, energy is released. That released energy is nothing but electron affinity, you must understand. So the affinity, if it is Cl minus, and the energy is basically released, right? It is heat evolved. It is basically evolved. So if you wanted to write it outside, then delta H is minus E, right? That is kilocalories. That is exothermic reaction, you must understand. That is step 4. Now come on, now what happens? You have the Cl minus ready for you, and the sodium ions ready for you. So both will combine now, and no one can stop them. No one can stop them. And when a mole of sodium ions and a mole of Cl minus ion combine, the energy released is nothing but the lattice energy. So now the final step is step 5. Step 5. Here is a mole of sodium ions which you prepared, and here is a mole of Cl minus you prepared, and you get a mole of NaCl formed. No one can stop them. And one mole of positive ions, 1 mole of negative ions combining to form a 1 mole of ionic crystal. The energy released is nothing but the lattice energy, and it is exothermic. It's a natural love plus U. And this is exo, U, that's the lattice energy. That U is called the lattice energy, you must understand. The U is called the lattice energy, you must understand that. Right? And if you wanted to write it outside, then delta H is basically minus U kilocalories, and this is exothermic. Right? So what we are doing basically is we are determining the lattice energy of NaCl. Then you went into the lab and prepared the direct step here this way, right? And the above step is divided into 5 steps: ionization, sublimation, dissociation, and then you have electron affinity, right, of chlorine. And then you have the lattice energy, that is the 5th step, right? So 2 things are there on the board now. 1, the direct step, and the 5 theoretical steps. So you have in your, you can see here, this is a direct step, and this step is divided into 5 theoretical steps. Now next what? Now next what? Remember the aim, we are trying to determine what? The lattice energy of NaCl. So if I can rewrite all this very quickly, observe carefully here, is basically calculate lattice energy of NaCl, right? So what we are doing is basically we have put the direct step, which I'm rewriting again. That is the laboratory step, and that is sodium solid, chlorine gas exposed, and then you got NaCl plus heat evolved. And if you wanted to write it outside, we call this to be delta H is minus Q kilocalories. That is the direct step. And what we have done, this direct step is divided into 5 theoretical steps. 5 theoretical steps. And I wanted to write it very quickly. Then we can understand what to do next. So the first one is basically sublimation energy. Sublimation of sodium rather. So what you're doing, sodium solid, convert to sodium gas. For this you require energy, and if I can write it outside, it is plus S kilocalories, right? Plus S kilocalories. And remember, the other step is basically this, ionization energy of sodium. So if I can write this, then the sodium gas, I kick this electron out, and for that I supply energy. This is also endothermic, and the delta H is plus I kilocalories. You must understand, that is step 2. And the step 3 is basically dissociation of chlorine molecule. And in fact, we require only half molecule of chlorine, not full. So I take half chlorine molecule, divide it into 1 chlorine atom. 1 chlorine atom, for that I require D by 2, and if I can write it outside, it is plus D by 2 kilocalories. You must understand. That's step 3. And in step 4, then I have in step 4, write electron affinity of chlorine. Electron affinity of this chlorine. This chlorine which you have prepared. So add an electron, you got Cl minus, and now the heat is evolved. This is evolved. So the delta H is minus E kilocalories. You must understand, right? Now you look into this. This is 4 steps what we have written, in which the sodium ion is ready, and the chloride ion is also ready. The chloride ion is also ready, right? And finally, in the step 5, I call this to be lattice energy of NaCl. Now what is lattice energy of NaCl? You have 1 mole of sodium ions, a mole of Cl minus ions, and you get a mole of NaCl, and the energy is released. This is exo. And the U is lattice energy, so delta H is minus U kilocalories. This is where we stopped. This is where we stopped. Now the question is, next what? Next what? Remember, don't forget the aim. We are trying to calculate lattice energy of NaCl. So that means we need to find out U. This is theory. This is theory. From that, we should be actually in a position to find out what? Lattice energy. So for finding lattice energy of NaCl, we went to the lab first. And then we came back to the classroom. And then we are discussing splitting this above step into 5 steps. And this is where we stopped. So next what? Next what? Next what? What's next? How do you calculate U? So what I will do is, I wanted to introduce a law for you. We will apply that law to determine what? The lattice energy of NaCl. Well, I wanted to propose the law for you. With due respect to this person, I wanted to put it in inverted commas. Look here. What we do is, this is Hess's law of constant heat summation. Next is, what we will do, we will propose a law, and then what we will do is, we will apply the law. We will propose this law, and we will apply this law, and on application we can determine what? U. So what is this law telling? Let me first tell you orally. Hess's law states, if the reaction I want everyone's attention, please. I propose the law for you. If a reaction proceeds in single step or in several steps, and I repeat, if a particular reaction proceeds in a single step or in several steps, right, the energy released is same. And I repeat, if a reaction proceeds in single step or in what? Several steps, the energy released is absolutely the same. Is absolutely the same. It is same. And I wanted to write it in inverted commas. Reaction proceeding in single step or in several steps, energy released is same. Is basically same. You must understand. Inverted commas. Reaction proceeding in single step or in several steps, the sum total of all the energies will remain the same. Well, wonderful, great, great law. Then is basically referring to the single step is this step. And the several steps is referring to is 1, 2, 3, 4, 5. So you proceed in a single step or in several steps, the sum total. That's what he says, summation. Summation is sum. The sum total of the several steps which you are proposing in the classroom, the energy released as a sum total of all the steps which you are proposing in the classroom will be equal to the energy released when you go and directly do it. If this is the case, let us apply then. So what I'll do, applying Hess's law, the single step energy is minus Q kilocalories. This is the single step energy which is released. I am taking heats of reaction, not the heat evolved, the one which I have written it at the bottom. So minus Q kilocalories, that is the single step energy, which should be equal to the sum total of all the 5 steps. All the 5 steps. And I want to take the delta H values here. So it will be equal to S plus I, S plus I plus D by 2 minus E and minus U. I have applied Hess's law. You yourself told me that whether the energy released is in a single step or in several steps, the energy released is same. So what I'll do is the total energy released in all the steps, 1, 2, 3, 4, 5, summation, addition. So the total or the net energy released in the 5 steps must be equal to the energy which is released in the single step. So I equate it. So I have an equation. But don't forget the aim. What are we doing? What are we doing? We need to determine what? The lattice energy. So we need to determine U. We must be determining U. So what I'll do, let me take U to this side and take all this that side. Q minus Q going that side is plus Q plus I plus D by 2 minus E. And this is the equation to determine what? The lattice energy. You must understand. Add everything and subtract what? Electron affinity. That will be a question in the exam. He will give you, sometimes what happens is he will give you lattice energy, he will give you Q, you will give you S, he will give you I, D by 2 and ask what? Electron affinity. That's a question in the exam. Otherwise, he'll give you all these questions, all these values and ask you what? Lattice energy. Lattice energy, you must understand. Right? So, what is Hess's law telling me is the energy released in single step or in what? Several steps. The summation of the energies released in all the theoretical steps will be equal to the energy released in the experimental step. Using that, I have determined what? U. right? That is how I determine what? The lattice energy of NaCl. Now what we will do is basically we can put all these pictorially, and we will make a pictorial representation of all these steps, including the direct step, including all these steps in one go. One go. What I will do is, it seemed to be laborious for us, so what we will do is, we'll make a pictorial representation of this. We'll make a pictorial representation of this. And that pictorial representation, observe, this we will actually exhibit in the form of a cycle, right? So what I'm trying to do is the Born-Haber cycle. The Born-Haber cycle. Born-Haber cycle. So this entire single step and the several steps are put it in the form of a cycle, which I call this to be a Born-Haber cycle, right? Everything in one go. Everything in one go in a pictorial representation. Now look into this, how the cycle looks like. This is the direct step. This is the solid. And you basically treat it with chlorine gas. Then you got NaCl. Right, and the energy released is plus Q, and if you wanted to write it outside, it is minus Q kilocalories. That is a direct step, right? Now what I'll do, I'll go this way and prepare sodium ions and chloride ions and see that you come back again there, because after all, it's a cycle. So what I'm doing, this sodium is now sublimated. This is sublimated. Right? And the energy released is pluses. The delta H is what? Pluses. Because you have given what? Energy. Right? So this, you got sodium, and then what you do is you remove an electron from this. So again you spend some energy, ionization energy, and then you have Na plus formed. You removed an electron. So now the Na plus is ready for you. Now what you're doing, this chlorine is now dissociated into chlorine atoms, and for this you provided D/2. We'll make it short, such that the cycle looks having a perfect decorum. Right, let's make it short. This giving you Na plus. Right, for this you spent energy, that is plus I. The sodium is ready now, and we wanted chlorine atoms. So what you do, this chlorine atoms, you got it, and you spent plus D/2, right? Plus D/2, and this chlorine is now given an electron, and this forms basically, this forms, right, Cl minus. This forms basically Cl minus, you must understand. And for this, the energy is released, that is plus E. That is plus E. Right? So if I can extend this, then it's like this, that you know, if we can extend this and write it properly, this entire pictorial representation, it looks like this. First, what you do, you take sodium, you convert this into sodium gas, and from that you remove what? Na plus. To conversion, it is pluses. For this you require plus I, that is ionization energy. The sodium is ready now, and then you have half chlorines, right? Half chlorines here. Then half chlorines. You dissociate this into what? Chlorine atoms. Right? Dissociate this into what? Chlorine atoms. Half chlorines. Right? This you must be dissociating into chlorine atoms. And for that you require D/2. And then you add an electron. Then it forms what? Cl minus. Then it forms what? Cl minus. And the energy released is what? Minus E. Minus E. So look into the cycle. Sodium formed Na, and Na is forming Na plus. This half chlorine is giving you chlorine atoms, and then you added an electron to this and got converted to what? Cl minus, you must understand. And now you have Na plus and Cl minus together, and they will form basically the NaCl solid, and the energy is released, that is plus Q, or I can write this to be minus Q. Now what is happening in this cycle is basically, what has happened in this cycle is basically you have your direct step at one place. That is a direct step. You go this way, you go this way, you go this way, come this way, come this way, the energy released is same. That means minus Q of the direct step will be equal to the plus S, plus I, plus D by 2, minus E, minus U. Single step energy must be equal to the sum total of all the energies shown here. So the U will be equal to Q plus S plus I plus D by 2 minus E, and that is nothing but the lattice energy. This way of representing things is nothing but the Born-Haber cycle for NaCl, you must understand. That is a Born-Haber cycle for NaCl, you must understand that. So what is Born-Haber cycle is basically, it is showing for you both the direct step as well as the theoretical steps, and then you can determine what. And this is what? This is basically after applying Hess's law. After applying what? Hess's law, you must understand. Right? So this is Born-Haber cycle, as it is a cycle because direct step, go this way, come this way, again you will end up at what? This one. You must understand. That is Born-Haber's cycle. Now remember small definitions and some laws because it's important. Remember this. 1 mole of positive ions plus 1 mole of negative ions brought together to form 1 mole of a lattice, then the energy released is U. That is nothing but the lattice energy. For example, if I wanted to apply this, a mole of Na plus, a mole of Cl minus. What do you mean by this? This is 6 into 10 power 23 sodium ions and 6 into 10 power 23 Cl minus ions brought together from infinity. They are brought together from infinity to form a mole of NaCl. To form a mole of what? NaCl. Then the energy released is called U. It's called U. That is nothing but the lattice energy. If you wanted to apply for something else, then it is like this. Suppose if you wanted to know what is lattice energy of this, then it's basically a mole of magnesium ions and 2 moles of chloride ions. That is 6 into 10 power 23 plus 2 into 6 into 10 power 23 chloride ions combining, giving you a mole of MgCl2, then the energy released is U. That's nothing but the lattice energy, you must understand. Similarly, if you wanted to have AlCl3, it is a mole, that is 6 into 10 power 23 aluminiums and 3 into 6 into 10 power 23 chloride ions giving you, then the lattice energy is U for a mole of what? AlCl3, you must understand. So you should have a clear picture of what is what? Lattice energy.